November 14th, 1942. Kummersdorf Proving Ground, 60 kilometers south of Berlin. German ordnance engineers gathered around a captured American weapon that looked absurdly simple. A steel tube, open at both ends, no breech mechanism, no recoil system, no sophisticated sighting apparatus. Just a hollow pipe with a wire grip and a crude electrical trigger mechanism. The weapon weighed 20 pounds. A German anti-tank rifle, designed to accomplish the same mission, weighed nearly twice that and required specialized training to operate effectively. The Americans called it a bazooka, apparently named after some comedian's musical instrument. German intelligence had recovered several examples from Soviet forces on the Eastern Front who had received them through Lend-Lease shipments. Additional specimens came from the fighting in Tunisia, where inexperienced American troops had deployed them against German armor during Operation Torch. The initial intelligence reports seemed almost dismissive. American infantry anti-tank weapon, caliber 60 mm, effective range approximately 120 meters, fires rocket-propelled shaped charge warhead, requires two-man crew for optimal operation. What the intelligence reports failed to convey was the philosophical revolution this crude tube represented. The Germans, masters of precision engineering and sophisticated weapons design, were about to confront a weapon that violated every principle of their military-industrial culture. The bazooka succeeded not through technical sophistication but through brutal simplicity, not through precision manufacturing but through mass production, not through specialized training but through intuitive operation. The weapon represented everything German military tradition dismissed as crude American pragmatism. And it worked. The test began with standard procedure. A section of armor plate, 100 millimeters thick, positioned at 50 meters distance, rolled homogeneous armor, the type used on most German tanks. The German engineer assigned as gunner had received only brief instruction. Shoulder the tube. Ensure the loader stands clear of the rear blast area. Aim using the simple wire sight. Pull the first trigger to cock the magneto. Pull the second trigger to fire. The M6 rocket, weighing 3.5 pounds, slid into the rear of the tube. The loader connected the wire terminal to the firing circuit. Ready. The trigger mechanism generated a small electrical current. The rocket motor ignited. For a fraction of a second, flame and smoke erupted from both ends of the tube. The rocket accelerated down the tube, still burning, and emerged at approximately 110 meters per second. 2 meters beyond the muzzle, the rocket motor burned out. The projectile continued in stable flight, guided by 4 spring-loaded fins that deployed immediately after launch, covering the 50-meter distance in less than half a second. The shaped charge warhead struck the armor plate and detonated. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. When German engineers examined the target plate, they found a hole. Not a crater, not a dent. A hole. The shaped charge had burned through 100 millimeters of hardened steel armor, a weapon that looked like a toy, operated by soldiers with minimal training, firing rockets that appeared crude compared to German precision munitions, had just defeated armor that required German anti-tank guns weighing hundreds of pounds to penetrate at similar ranges. The psychological impact of this discovery rippled through the German ordnance establishment with profound implications. To understand why this simple tube shocked German engineers, you need to understand what Germany possessed in November 1942 for infantry anti-tank defense. The standard weapon was the Panzerschreck 39 anti-tank rifle, a precision-manufactured bolt-action weapon firing tungsten-core armor-piercing ammunition. The rifle weighed 35 pounds. It required a 2-man crew, extensive training, and perfect conditions to achieve any effectiveness. Against early war tanks like the Polish 7TP or Soviet BT-7, the Panzerschreck performed adequately. Against the Soviet T-34 or American Sherman, it was effectively useless. The tungsten core projectile could not penetrate the frontal armor of these medium tanks at any practical combat range. Germany had developed more capable weapons. The 28mm SPZB-41, a tapered-bore anti-tank rifle that used squeeze-bore technology to achieve remarkable velocity and penetration. But the weapon required tungsten projectiles that Germany could not produce in adequate quantities after losing access to tungsten supplies from Asia and occupied territories. Production remained limited throughout the war. Against the thickest armor, Germany deployed the 75mm Pak-40 anti-tank gun, a magnificent weapon that could destroy any Allied tank at ranges exceeding 1,000 meters. But the Pak-40 weighed 3,300 pounds in firing position. It required a truck or half-track to tow it into position. It needed a trained crew of 6 men operating in coordinated precision. Deployment took minutes under ideal conditions. Under combat stress, against rapidly advancing armor, those minutes could prove fatal. The weapon exemplified German design philosophy: sophisticated, powerful, expensive, difficult to produce in the quantities required for the vast frontages Germany now defended from Leningrad to North Africa. German industry had also developed the Raketenwerfer 43 Pupchen, an 88mm rocket launcher mounted on a wheeled carriage similar to conventional anti-tank guns. The weapon fired an excellent-shaped charge warhead, capable of penetrating armor exceeding German tank gun capabilities. But the Pupchen weighed 330 pounds. It required a crew of 3 to 5 men. It needed a vehicle to transport it. Deployment remained complex. Production remained limited. The weapon represented typical German engineering: excellent specifications on paper, practical limitations in field deployment. What Germany lacked, and desperately needed by late 1942, was a simple, lightweight, mass-producible anti-tank weapon that individual infantry soldiers could carry and employ without extensive training. A weapon that gave every infantry platoon the capability to engage enemy armor at effective ranges, without requiring specialized anti-tank units or towed guns. The Americans had apparently solved this problem with a hollow steel tube and a rocket motor. The implications for German defensive doctrine were profound. The implications for German industrial planning were catastrophic. The captured bazookas underwent systematic evaluation throughout November and December 1942. German engineers disassembled the weapon completely, documenting every component, measuring every dimension, analyzing every design choice. What they discovered validated their initial assessment. The weapon was almost insultingly simple. The launch tube consisted of welded sheet steel, minimal machining, no precision tolerances. The weapon could be manufactured by semi-skilled workers using basic equipment. American production methods emphasized speed and quantity over precision and quality, exactly the opposite of German manufacturing culture. The firing mechanism used a basic magneto system, similar to those in German field telephones. Pulling the trigger rotated a small generator that produced the electrical current to ignite the rocket motor. Simple, reliable, inexpensive. The sighting system consisted of wire frames aligned by eye, no optical elements, no precision adjustments, crude but adequate for the weapon's effective range of 120 meters. American soldiers apparently aimed by instinct and experience rather than calculated ballistics. The rocket itself represented real innovation. The M6 rocket used a shaped charge warhead, technology the Germans understood well. German scientists had pioneered shaped charge research in the 1930s, developing hollow charge technology that focused explosive force into a narrow jet capable of penetrating armor far exceeding the explosive's weight. But American engineers had packaged this technology into a rocket-propelled projectile that could be launched from an open tube without any of the complex mechanisms required for conventional guns. The shaped charge principle relied on a specific physical phenomenon. An explosive charge placed behind a conical metal liner, typically copper, and detonated from the rear creates a hypervelocity jet of metal particles. This jet travels at velocities approaching 8,000 meters per second, carrying kinetic energy sufficient to penetrate steel armor through sheer force. The penetration depth depends primarily on the cone's geometry and the charge diameter. Larger diameter equals deeper penetration. The American 60mm rocket achieved penetration roughly equivalent to 1.5 times its diameter, approximately 90 to 100 millimeters under optimal conditions. German test firings confirmed the American claims. At 50 meters, the M6 rocket penetrated 100 millimeters of rolled homogeneous armor at 90-degree impact angles. At 30-degree angles from perpendicular, representing typical combat situations where rounds struck sloped armor, penetration reduced to approximately 75 millimeters. Still adequate to defeat most German tank side armor and all Allied tank frontal armor from reasonable engagement ranges. The American weapon, for all its crudity, worked. German engineers identified weaknesses. The battery-powered firing system in early M1 bazookas proved unreliable under field conditions. Batteries failed in cold weather. Moisture caused electrical shorts. Combat damage to the battery compartment rendered the weapon inoperative. American forces apparently experienced significant problems with premature detonations when rockets stuck in the launch tube due to manufacturing tolerances that German industry would never accept. Some American soldiers had been killed or injured when defective rockets exploded inside the tube during firing. The rocket motor design also revealed American compromise between effectiveness and simplicity. The motor continued burning after the rocket left the tube, creating a dangerous blast zone extending 2 meters behind the weapon. Any soldier or friendly personnel in that zone risked serious burns. German soldiers were trained to avoid standing behind firing weapons, but the bazooka's blast signature made concealment nearly impossible. The smoke and flame betrayed the shooter's position immediately, inviting return fire. These weaknesses mattered less than the fundamental capability. The Americans had fielded a weapon that gave infantry forces genuine anti-tank capability in a package that weighed 20 pounds and required minimal training. German soldiers facing Soviet armor on the Eastern Front needed such a weapon desperately. German infantry defending against Allied advances in North Africa needed it urgently. And most critically, German industry, stretched thin supporting a three-front war while suffering increasing Allied bombing, could theoretically produce such a weapon in vast quantities using minimal strategic materials. The decision to copy the American bazooka was made quickly, probably in late December 1942 or early January 1943. But German engineering culture could not simply copy American design without improvement. The German version, designated American Panzerschreck 43, quickly became known as the Panzerschreck, tank terror. The name itself reflected German attempts to boost troop morale through aggressive weapon nomenclature, a psychological compensation for increasingly desperate strategic circumstances. German engineers made several significant modifications to the basic bazooka concept. First, they increased the caliber from 60 mm to 88 mm. This decision reflected existing German rocket development. The Pupchen already used an 88 mm rocket with excellent shaped charge performance. German factories already produced the RPZBGR 4312 warhead and rocket motor for that weapon. Rather than develop an entirely new rocket, engineers simply adapted the existing 88 mm rocket to fit an open-tube launcher modeled on the American bazooka. This seemingly practical decision created problems. The 88 mm rocket weighed 7.25 pounds, more than twice the weight of the American 60 mm rocket. The larger warhead required a proportionally larger and heavier launch tube. The final Panzerschreck design weighed 24 pounds empty, compared to 13 pounds for the American M1A1 bazooka. The weight difference, while seemingly modest, affected practical deployment. American soldiers could carry and maneuver their bazooka more easily. German soldiers found the Panzerschreck more cumbersome, particularly in close combat or rapid movement situations. The increased caliber did provide advantages. German test data claimed the 88 mm shaped charge could penetrate 200 to 30 mm of vertical armor at perpendicular impact. At 60-degree angles from perpendicular, typical of combat against sloped armor, penetration remained at 100 to 60 mm. These figures exceeded American bazooka performance by substantial margins. The Panzerschreck could reliably, penetrate any Allied tank from virtually any angle at its effective range. German engineers replaced the battery-powered firing system with a magneto, addressing one of the bazooka's key weaknesses. The magneto system proved more reliable under field conditions and eliminated battery maintenance requirements. This improvement reflected German engineering emphasis on reliability and reduced maintenance burden. In this instance, the German modification represented a genuine improvement over American design. But German engineers also created new problems. The 88mm rocket motor, designed for the breech-loading Pupchen, required modification to function in an open-tube launcher. The modified motor burned longer than the American rocket motor. The Panzerschreck rocket continued burning for approximately 2 meters after leaving the launch tube, compared to the American rocket that burned out within the tube. This extended burn created a massive backblast and enormous smoke signature. The blast and smoke proved so severe that Panzerschreck crews required protective equipment. German quartermasters issued fireproof ponchos and gas masks without filters to protect crews from burns and smoke inhalation. Even with protective gear, firing the Panzerschreck remained an unpleasant and dangerous experience. The weapon earned the nickname Ofenrohr, stovepipe, from the enormous smoke clouds it produced. Crews learned quickly that firing revealed their position instantly, requiring immediate displacement to avoid return fire. In February 1944, German engineers added a blast shield to the Panzerschreck design, creating the RPZB-54 variant. The shield, a curved steel plate positioned between the gunner and the launch tube, provided some protection from the rocket's backblast. The modification added weight, increasing the weapon to 24 pounds empty, but improved crew safety sufficiently to justify the penalty. Even with the blast, shield, operating a Panzerschreck, remained significantly more hazardous than operating an American bazooka. Production began in early 1943. German factories in the Reich and occupied territories manufactured Panzerschrecks using the simplified production methods learned from studying the American weapon. The Hussag factory in Meuselwitz produced significant quantities. Belgium factories also manufactured the weapon under German supervision. By late 1943, Panzerschrecks reached frontline units in substantial numbers. German infantry finally possessed a portable anti-tank weapon with genuine effectiveness against Allied armor. The weapon proved devastatingly effective in situations matching its design parameters. Panzerschreck teams set up in ambush positions could destroy Allied tanks with single shots. German defensive doctrine evolved to incorporate Panzerschreck tactics specifically. Infantry units positioned Panzerschreck teams in staggered positions, no more than 115 meters apart along likely armor approach routes. This spacing ensured attacking armor faced anti-tank fire from multiple directions at ranges not exceeding 69 meters, well within the weapon's effective engagement envelope. German tactical guidance emphasized targeting tank side and rear armor whenever possible. While the Panzerschreck could penetrate Allied tank frontal armor, side and rear shots guaranteed kills with single hits and reduced the risk of non-penetrating strikes against sloped surfaces. Infantry learned to allow tanks to pass their concealed positions, then engage from behind where armor was thinnest and ammunition stowage most vulnerable. These tactics, crude but effective, proved particularly devastating in confined terrain like Normandy's Bocage country or Italian mountain passes where Allied tanks had limited maneuver room. But effectiveness in ideal conditions masked deeper problems. The Panzerschreck, for all its power, remained fundamentally reactive. German forces used it in defensive operations, waiting for Allied tanks to enter engagement range. The weapon could not support offensive operations effectively. The weight, bulk, and backblast signature made the Panzerschreck poorly suited for mobile warfare. German soldiers advancing across open terrain could not effectively employ the weapon while under fire and moving forward. The Panzerschreck exemplified German strategic circumstances by 1943. Powerful defensive weapons, inadequate resources for offensive action. Production statistics reveal the extent of Germany's commitment to the Panzerschreck concept. Exact production figures remain uncertain, but estimates suggest Germany manufactured somewhere between 300,000 and 400,000. Panzerschrecks between early 1943 and war's end in May 1945. This represented substantial industrial commitment for a nation facing increasing resource shortages and Allied bombing campaigns. The investment reflected a desperate need for effective infantry anti-tank weapons as Allied armoured forces grew in strength and Germany's own tank production struggled to meet demand. The cost comparison revealed typical German industrial challenges. A single Panzerschreck cost approximately 70 Reichsmarks to manufacture, far less than conventional anti-tank guns costing thousands of Reichsmarks. The simplified design and minimal precision requirements meant Germany could produce Panzerschrecks faster and cheaper than almost any other anti-tank weapon. But Germany still could not produce enough. German infantry units on all fronts reported chronic shortages of Panzerschrecks throughout 1944 and 45. Divisions authorized for multiple Panzerschreck teams per company often fielded only a fraction of authorized strength. Ammunition availability created additional problems. Each Panzerschreck rocket cost significant resources to manufacture despite simplified production methods. The 88mm shaped charge warhead required copper for the cone liner, a strategic material Germany increasingly lacked. The rocket motor required propellant chemicals that competed with artillery ammunition and other munitions for limited production capacity. German logistics struggled to deliver adequate ammunition to forward units. Panzerschreck teams in defensive positions often possessed only a handful of rockets, forcing them to hold fire until absolutely certain of achieving kills. Allied forces learned to counter Panzerschreck tactics through practical experience. American tank crews added improvised armor to their vehicles. Sandbags piled on hull fronts and sides. Spare track sections welded to turrets. Logs strapped to hull sides. The improvised armor proved ineffective against Panzerschreck hits. The shaped charge penetrated sandbags and wooden logs without significant performance degradation. But the improvised armor provided psychological comfort to crews who felt desperately vulnerable to German anti-tank weapons. More effective countermeasures focused on combined arms tactics. American doctrine emphasized never sending tanks forward without infantry support. Infantry cleared suspected Panzerschreck positions before tanks advanced. Artillery fire saturated areas where Panzerschreck teams might hide. Tactical air support attacked any position that revealed itself by firing. The massive Allied advantage in artillery and air power meant that Panzerschreck teams, once they fired and revealed their positions, rarely survived long enough to engage multiple targets. The psychological effect on German morale of possessing the Panzerschreck cannot be understated. German infantry, who had felt helpless against Allied armor, suddenly possessed a weapon that could kill tanks. This psychological empowerment mattered enormously for soldiers facing overwhelming material odds. The knowledge that a small team with a simple weapon could destroy a 30-ton Sherman tank provided some measure of confidence to troops otherwise outgunned and outproduced by Allied industrial might. But the Panzerschreck could not change fundamental strategic realities. Germany faced enemies capable of replacing destroyed tanks within weeks. Allied industrial production delivered new Shermans, Cromwells, and T-34 seconds faster than German Panzerschreck teams could destroy them. German factories struggled to maintain production of their own tanks while supporting the war effort across multiple fronts. The Panzerschreck gave German infantry the capability to fight Allied armor effectively. It could not provide the industrial capacity to win a war of attrition against nations producing tens of thousands of tanks annually. The comparison between the Panzerschreck and its American inspiration reveals fundamental differences in military-industrial philosophy. The Americans designed the Profilation bazooka as adequate rather than optimal. 60mm diameter provided sufficient penetration against most Axis armor while allowing lightweight design and simplified production. The battery firing system, while problematic, worked adequately under most conditions and required no specialized components. The weapon prioritized mass production and ease of use over maximum performance. German engineers, constrained by military tradition and engineering culture, could not accept adequacy. They needed superiority. the 88mm caliber magneto firing system, and eventual blast shield all represented attempts to improve on American design. Some improvements worked. The magneto proved more reliable than batteries. The increased warhead size provided penetration exceeding practical requirements against Allied armor, but improvements came at cost: increased weight, increased production complexity, increased blast signature. The German weapon, while more powerful, was less practical than its American inspiration. This pattern repeated across German weapons development throughout the war. German engineers consistently prioritized technical superiority over practical deployment considerations. The result was weapons that impressed on paper and in controlled conditions but struggled under actual combat circumstances. The Panther tank exemplified this with catastrophic final drive failures. The Ferdinand tank destroyer with inadequate defensive armament, the Panzerschreck with its dangerous backblast and smoke signature. German weapons worked magnificently when conditions matched design parameters. Real combat rarely provided such ideal circumstances. American weapons development followed opposite priorities: adequacy over excellence, reliability over sophistication, mass production over precision manufacturing. The bazooka perfectly embodied this philosophy. Was it the best possible anti-tank weapon? Absolutely not. Could American industry produce it in vast quantities? Yes. Could minimally trained soldiers operate it effectively? Yes. Would it function reliably under harsh field conditions? Mostly yes, with improvements addressing identified weaknesses. These practical virtues mattered more than impressive specifications because modern industrial warfare rewarded sustainable mass production over individual weapon excellence. The Germans recognized this truth intellectually. Intelligence reports and after-action analyses repeatedly identified Allied advantages in industrial production and logistics sustainability. German military planners understood they faced enemies capable of absorbing losses and replacing equipment faster than Germany could inflict attrition. But German military culture, rooted in Prussian traditions emphasizing individual excellence and technical sophistication, struggled to adapt operational doctrine and industrial planning to this reality. The decision to copy the American bazooka represented a rare instance, where German pragmatism overcame cultural bias toward technical sophistication. The Panzerschreck, despite German modifications, remained fundamentally an American concept. Simple, mass-producible, operated by regular infantry rather than specialists. The weapon succeeded precisely because it violated traditional German design philosophy. Had German engineers designed an infantry anti-tank weapon from first principles, unconstrained by the captured American example, they likely would have produced something far more sophisticated, far more expensive, and far less practical for the strategic circumstances Germany faced in 1943. The irony was profound and apparently lost on German leadership. Germany's finest engineers, trained in world-class technical universities, operating with access to advanced research and sophisticated manufacturing capability, achieved their most successful infantry anti-tank weapon by copying a crude American design. The weapon that best met German needs came not from German innovation, but from American pragmatism. The philosophical implications threatened core assumptions about Aryan technical superiority and the supposed advantages of German systematic engineering approach. This cognitive dissonance appeared in German documentation and propaganda about the Panzerschreck. Official reports acknowledged the American origin but emphasized German improvements and superior performance. Propaganda materials presented the weapon as an example of German engineering excellence, minimizing or omitting American origins. The need to maintain myths about German technical superiority outweighed honest assessment of how Germany achieved what limited successes remained possible by late war. The American response to the Panzerschreck revealed different priorities. When intelligence reports described the German copy with increased caliber and improved penetration, American ordnance departments initiated their own upgrade program. The result was the M20 Super Bazooka, fielded in 1945 with 89mm caliber and penetration, approaching 280mm. but the Super Bazooka arrived too late for significant World War II deployment. Most American bazookas used throughout the European campaign remained the original 60mm M1A1 and improved M9 variants. This delay reflected American confidence that existing weapons remained adequate for the mission despite German improvements. The M9 bazooka could penetrate up to 125mm, with improved M6A3 rockets, sufficient to defeat most German tank side armor and adequate against many frontal armor sections. American doctrine emphasized combined arms tactics rather than individual weapon superiority. Infantry with bazookas worked alongside tank destroyers mounting 3-inch or 90mm guns, artillery capable of destroying any tank with direct hits, and tactical air support that could attack German armor throughout the depth of the battlefield. German forces lacked these combined arms advantages by 1944. Luftwaffe air superiority had vanished. German artillery struggled with ammunition shortages and increasing Allied counter-battery effectiveness. German tank destroyer units were spread thin across vast frontages. The Panzerschreck became German infantry's primary anti-tank weapon, not by choice but by necessity. The weapon had to compensate for systemic weaknesses in German combined arms capability. No infantry anti-tank weapon, regardless of sophistication, could fill that void effectively. The ultimate measure of the Panzerschreck's success was not in specifications or test range performance, but in its effect on Allied operations. Did the weapon significantly delay or hinder Allied advances? Did it impose unsustainable casualties on Allied armoured forces? Did it force major changes to Allied tactical doctrine or operational planning? The evidence suggests modest effects at tactical level without significant strategic impact. Allied after-action reports from Normandy through Germany document Panzerschreck engagements regularly. Allied tank losses to German anti-tank weapons, including Panzerschrecks, Panzerfausts, and towed anti-tank guns, remained steady throughout the final year of war. But Allied production replaced losses faster than German weapons could inflict them. American armoured divisions that suffered heavy casualties in one engagement received replacement tanks within days or weeks. British and Canadian armoured units maintained operational strength through efficient logistics and rapid repair of damaged vehicles. German Panzerschreck teams achieved impressive kill counts in defensive engagements. Individual teams sometimes destroyed multiple Allied tanks in single actions, particularly in urban terrain or restrictive geography favouring ambush tactics. These tactical successes, celebrated in German military records and propaganda, could not alter strategic realities. For every Allied tank destroyed by a Panzerschreck, American factories produced 10 replacements. For every Panzerschreck team that successfully engaged Allied armour, Allied artillery or air power destroyed 3 others before they could fire. The mathematical certainty of German defeat became clearer with every passing month. By early 1945, even the most fanatical German commanders recognized that no weapon, regardless of effectiveness, could compensate for the overwhelming material superiority Allied forces possessed. The Panzerschreck gave German infantry fighting chance against individual Allied tanks. It could not provide the industrial base, logistics, infrastructure, or manpower necessary to win a war of attrition against enemies producing war material at rates Germany could never match. The captured American bazooka that German engineers examined at Kummersdorf in November 1942 represented more than just a new weapon design. It symbolized fundamentally different approaches to modern warfare. The Americans built weapons optimized for mass production and practical deployment rather than technical perfection. They accepted adequacy sustained over long campaigns rather than excellence in individual engagements. They prioritized logistics, industrial capacity, and sustainable operations over tactical sophistication. German military culture, for all its genuine excellence in many areas, struggled to adapt to these industrial-age priorities. Germany continued designing sophisticated weapons when simpler designs would have served better. Germany continued emphasizing individual weapon superiority when overwhelming numerical advantage mattered more. Germany continued trying to achieve through technical excellence what could only be won through industrial capacity and logistics sustainability. The Panzerschreck represented a rare exception where German pragmatism overcame cultural bias. But one pragmatic weapon could not compensate for systemic failures in strategic planning and industrial mobilization. The weapons deployed to combat units throughout spring and summer 1944, arriving just in time for the greatest test German forces would face. Allied invasion of Fortress Europe. Normandy, June 1944. The Bocage country of northwestern France provided ideal terrain for Panzerschreck employment. Ancient earthen hedgerows, thick vegetation, narrow sunken lanes created countless ambush positions where German infantry teams could lie concealed until Allied armour advanced within effective range. The densely confined terrain limited Allied visibility and manoeuvre options while maximising German defensive advantages. German tactical doctrine called for Panzerschreck teams to establish positions in staggered trenches, separated by no more than 115 metres. This spacing ensured attacking armour faced anti-tank fire from multiple directions at ranges not exceeding 69 metres, well within the weapon's effective envelope. Infantry learned to allow Sherman tanks to pass concealed forward positions, then engage from behind, targeting the thinnest side and rear armour where ammunition stowage remained most vulnerable. The tactics proved devastatingly effective in the narrow confines of Normandy's hedgerow country. German teams set up roadblock ambushes along wooded trails, attacking Allied tanks as they halted at obstacles or intersections. The confined terrain prevented rapid manoeuvre that might have allowed Allied armour to escape the kill zones. Once Panzerschreck teams opened fire, Allied tanks found themselves trapped in narrow lanes with limited visibility and nowhere to retreat. Under ideal conditions, Panzerschrecks proved enormously effective. A single shot could usually knock out an enemy tank. Canadian tanker Stanley Sislowski of the Perth Regiment, 11th Infantry Brigade, 5th Armoured Division, described the weapon's destructive power. German paratroopers fired on lead tanks with their extremely effective Panzerfausts and Panzerschrecks, both much feared by Allied tank crews. Later, Allied forces passed two Shermans jammed together. The front tank's turret was blown off and lying several yards to the side, giving good indication of the destructive power of shaped charge anti-tank bombs. But effectiveness came with severe limitations that Allied forces learned to exploit. The enormous smoke and dust generated during firing gave away Panzerschreck team positions immediately. These clouds revealed locations to enemy infantry and tanks, forcing rocket crews to move fast after launching or risk being killed by enemy small arms fire. The relatively short 180-metre maximum effective range meant Allied forces engaging from beyond that distance remained safe from Panzerschreck fire. The weapon's backblast created additional tactical constraints. Firing from inside closed spaces like bunkers or houses filled rooms with toxic smoke and revealed firing locations immediately. Urban combat, while providing cover and escape routes, required careful position selection to avoid trapping crews in smoke-filled buildings. The protective equipment required for safe operation, heavy gloves, fireproof ponchos, gas masks without filters, further reduced crew mobility and situational awareness during combat. Allied countermeasures evolved rapidly. Allied armoured units frequently attempted to add improvised protection to their tanks. Sandbags, spare track units, logs, and metal mesh resembling German Schürzen auxiliary plates. Tank crews believed these measures would provide protection against shaped charge warheads. In practice, about 1 metre of air gap was required to substantially reduce the penetrating capability of Panzerschreck rockets. Thus, skirts and sandbags proved ineffective. The improvised armour provided psychological comfort without meaningful protection. More effective Allied tactics focused on combined arms coordination. American doctrine emphasized never advancing tanks without infantry support. Infantry cleared suspected Panzerschreck positions before armour moved forward. Artillery fire saturated areas where anti-tank teams might hide. The massive Allied advantage in artillery meant that Panzerschreck teams, once they revealed positions by firing, rarely survived to engage multiple targets. Forward observers called concentrated fire missions within minutes, destroying German positions before crews could displace. Air superiority provided overwhelming Allied advantage. Tactical aircraft armed with rockets and bombs attacked any position that revealed itself. More importantly, air interdiction targeted German supply columns, fuel trucks, repair facilities, and supporting infrastructure sustaining Panzerschreck operations. German forces learned to move primarily at night to avoid air attack, further straining already fragile logistics and exhausting troops who needed rest. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Panzerschreck deployment to other theatres followed similar patterns. In 1944, Germany provided Panzerschrecks to Finland, which used them to great effect against Soviet armour. The Finnish name for the weapon was Panssarikohu, literal translation of the German name. Finnish forces, experienced in defensive warfare against Soviet armour since the Winter War, integrated the weapons into existing anti-tank doctrine effectively. The relatively static nature of Finnish defensive operations suited Panzerschreck tactical employment better than the mobile campaigns in Western Europe. The Italian Social Republic and Hungary also used the Panzerschreck. Several Italian units became known as skilled anti-tank hunters. Hungarians used the weapon extensively during Exe Dik, Operation Spring Awakening. The final major German offensive in March 1945 saw Hungarian Panzerschreck teams engage Soviet armour around Lake Balaton. The offensive failed within days against overwhelming Soviet numerical superiority and devastating artillery concentrations that destroyed German positions regardless of individual weapon effectiveness. The Eastern Front saw extensive Panzerschreck employment throughout 1944 and 45. German forces, defending against Soviet advances from Ukraine through Poland and into Germany itself, relied heavily on infantry anti-tank weapons, as conventional anti-tank gun units were destroyed or dispersed across vast frontages. Panzerschreck teams positioned in urban rubble created by Allied bombing and Soviet artillery provided some of the most effective resistance to Soviet tank advances during the war's final months. But individual weapon effectiveness could not compensate for systemic collapse. By late 1944, German logistics struggled to deliver adequate ammunition to forward units. Panzerschreck teams in defensive positions often possessed only a handful of rockets, forcing careful fire discipline and accepting that many Allied tanks would pass unengaged. German industry, despite simplified production methods, could not manufacture rockets fast enough to meet demand, while simultaneously supporting conventional artillery, tank ammunition, small arms, and countless other competing requirements. The copper required for shaped charge cone liners became increasingly scarce as Germany lost access to foreign sources and domestic production declined under Allied bombing. Substitute materials reduced penetration performance. Quality control deteriorated as Germany conscripted concentration camp labor and foreign workers into munitions production. Defective rockets caused premature detonations or failures to detonate, killing German crews or forcing them to engage at even closer ranges to guarantee hits. The psychological impact on German forces evolved throughout the war's final year. Initially, possession of effective anti-tank weapons boosted morale among infantry who had felt helpless against Allied armour. German soldiers gained confidence knowing they could destroy enemy tanks despite overwhelming material disadvantages. This psychological benefit mattered enormously for units facing Allied advances with inadequate tank support and declining air cover. But sustained combat eroded confidence, as German soldiers recognized fundamental realities. They could kill individual Allied tanks. They could not stop Allied offensives. For every Sherman destroyed by a Panzerschreck, Allied factories produced 10 replacements. For every successful ambush, Allied artillery destroyed 5 German positions. The knowledge that tactical success meant nothing without strategic capability to affect campaign outcomes created the despair visible in late-war German accounts. The comparison between German and Allied anti-tank weapon philosophy revealed contrasting approaches to modern warfare. Germany fielded the Panzerschreck and Panzerfaust as primary infantry anti-tank weapons, accepting that these were fundamentally defensive tools suited for ambush tactics. Allied forces deployed the bazooka as one element within comprehensive combined arms systems, including tank destroyers, towed anti-tank guns, artillery, and air support. No single weapon bore disproportionate responsibility for anti-tank capability. This systemic approach reflected Allied material advantages and operational doctrine. Allied forces could afford specialized weapons for specific missions because industrial capacity supported diverse production. Allied logistics could deliver multiple weapon types to forward units because transportation infrastructure remained intact. Allied tactical doctrine could employ combined arms because numerical superiority allowed concentration of different capabilities at decisive points. German forces, increasingly constrained by material shortages and strategic overextension, needed multi-purpose weapons and simplified logistics. The Panzerschreck represented a compromise between effectiveness and production feasibility. It provided genuine capability against Allied armor while remaining simple enough for Germany's declining industrial capacity to manufacture in substantial quantities. But the weapon could not compensate for systemic disadvantages in production, logistics, air power, and artillery that determined campaign outcomes. The ultimate measure of the Panzerschreck's success, or any weapon system, lies not in technical specifications or controlled test results, but in strategic impact. Did the weapon significantly affect campaign outcomes? Did it force major Allied operational adjustments? Did it impose costs disproportionate to resources consumed in its development and production? The historical record suggests modest tactical effectiveness without strategic significance. Allied forces advancing from Normandy to Germany suffered steady casualties to German anti-tank weapons, including Panzerschrecks, throughout the campaign. But these casualties never threatened operational objectives or forced major changes to Allied strategy. Allied replacement systems delivered new tanks, crews, and equipment faster than German weapons could inflict attrition. Allied combined arms tactics minimized exposure to close-range anti-tank fire through artillery preparation, air support, and infantry screening. German industry manufactured between 300,000 and 400,000 Panzerschrecks, representing a substantial commitment of increasingly scarce resources. The weapons gave German infantry genuine capability to engage Allied armor, but production consumed copper, steel, and chemical propellants that might have supported conventional anti-tank guns, artillery ammunition, or other systems with potentially greater strategic impact. Whether Germany made optimal resource allocation decisions regarding Panzerschreck production versus alternatives remains debatable among historians. The weapon that shocked German engineers in November 1942 ultimately became another example of how tactical capability cannot compensate for strategic failure. The simple American tube that German ordnance specialists found almost embarrassingly crude forced Germany to abandon traditional design philosophy and copy enemy technology. The resulting Panzerschreck, while more powerful than its American inspiration, still reflected fundamental American concepts: simplicity over sophistication, mass production over precision manufacturing, practical deployment over theoretical excellence. That German engineers had to learn these lessons from captured American equipment revealed how thoroughly German military-industrial culture had diverged from realities of mid-20th century warfare. The nation that pioneered internal combustion engines, invented shaped charge technology, developed sophisticated metallurgy and precision manufacturing, achieved its most successful infantry anti-tank weapon by copying American pragmatism. The irony was profound and apparently lost on German leadership committed to myths about Aryan technical superiority. The Americans, for their part, recognized German improvements and responded with their own upgrades. The M20 Super Bazooka, entering limited service in 1945, incorporated lessons from combat experience and German innovations. But American confidence that existing weapons remained adequate for the mission reflected a deeper understanding that individual weapon specifications mattered less than systemic advantages in production, logistics, and combined arms employment. Today, the Panzerschreck appears in military museums worldwide as testament to both German engineering capability and the limits of technical excellence divorced from strategic reality. The weapon represents a rare instance where German pragmatism overcame cultural bias toward sophistication. It demonstrates how even desperate circumstances and undeniable evidence could not fully transform military-industrial culture rooted in decades of tradition and institutional assumptions. Military historians and engineering students continue studying the Panzerschreck as an example of technology transfer under wartime pressure, successful adaptation of enemy innovations, and the relationship between tactical capabilities and strategic outcomes. The weapon serves as a reminder that modern warfare rewards sustainable mass production over individual excellence, that adequate performance deployed in overwhelming numbers defeats superior performance that cannot be maintained, that logistics and industrial capacity ultimately determine victory more than individual weapon specifications. The hollow steel tube that German engineers examined at Kummersdorf in November 1942 symbolized American military philosophy. Build weapons that work adequately rather than perfectly. Produce them in quantities that overwhelm enemies regardless of individual technical inferiority. Design for practical field deployment rather than ideal conditions. Accept that crude effectiveness beats sophisticated inadequacy. These principles, which German engineers initially dismissed as evidence of American technical backwardness, proved decisive in industrial warfare. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.